Thank you.
Excellent. Excellent. Well, thank you people for coming back again for a third go at this. And I hope you've been enjoying them, and as I have been. Today's, can everybody, is my slide showing? I think it is.
I can see it, yep.
All right, good. All right, so today we're going to be talking about, we have a little less material to cover than last time, but it's all a little harder than last time. So what I want everybody to encourage me to talk slower, because that way you can follow it better and I won't run out of material. So what we're talking about now is, suppose you got some training data and you had did a machine learning to learn a machine, and that machine does really well in your training data. And then the Google car that's learned to drive is going to drive out of the parking lot and see inputs that it's never seen before. And why can we at all hope that this will still work? And this proof is one of the only proofs I know in machine learning at all. And I learned it back when early days of me being a grad student. So it's a very elegant proof, and hopefully everybody can appreciate it. So just a reminder here, this is a classic graph from machine learning, where along here, the horizontal line, we're plotting M, which is how complex your machine is. And vertically, we're plotting how many errors does your machine have on the, right? So on the training data is this curve. And you can see the more complex the machine is, the more it's able to get all the right answers for the machine, for the training data. That certainly tends to not be a problem. The problem is overfitting, and overfitting happens when your machine is so powerful it can just memorize all the answers, but it hasn't learned anything. It hasn't seen a pattern in the data. It just wrote down the answers, and so it doesn't generalize. And the idea is to find a sweet spot in here where we're doing the best in the general data and the general inputs. And the reason it does, the intuition why it does better, is because the machine that's learning is somehow has to compress what it's learned into a smaller amount of space. And in order to do that, it needed to find some patterns in what it's learning. It has to see, why does this look like a cat? Why does this look like a face? And then when it sees data that it's never seen before, the hope that it will be able to generalize. All right, so I'm really big on compression and communication complexity. So let's talk a little bit about this, because I think it gives us a little intuition about what's going on. All right, so normally we have Alice who wants to send a message and Bob who wants to receive it. But somehow I got these cute little boys and they work fine. All right, and how do they sit? He says he has some message that he wants to transmit, and how does he do it? They send bits along the line, and the goal is, how do you get the message from A to B with communicating as few bits as possible? So in this case, the standard computer science thing is you take each letter as ASCII, and so each ASCII character uses 8 bits. And so that's how you take the message hello friend, and you can encode it into ASCII, and then you decode it back into hello friend. So, but now suppose what's being communicated is the presence of a particularly favorite truck. then maybe the boy could simply say truck, right? But the problem is there may be lots of trucks in the world, and we need to be clear which one we mean. And in general, if there are in objects and you want to send a message specifying one of those in objects, then you tend to need login bits for each one, right? Because there are 2 to the login messages that have login binary strings, and so that gives a separate message to each of your in objects. So on the other hand, the boys know each other and they're able to have schemes planned before the communication happens. And so maybe they know that, you know, this is a very special favorite truck. And so he could just say a short code like old red and they'll know what it means. And that takes fewer bits. And that's where compression comes in, right? We can encode into a smaller number of bits when the message being sent is somehow special. So in this case, it's not special. Suppose we have a completely random sequence of bits here, and we want to encode it and decode it so that those random bits are transmitted. Then Shannon proves using entropy that any random in-bit string is going to need in bits to communicate it. There's going to be no compression. If you have in bits of random independent bits of information, then you need to communicate in bits to get that message across. And that's all there is to it. Now, when can you compress is, well, maybe there's some pattern in the string, or there's somehow it's a favorite string. I personally find it a little more awkward when you're talking about, well, which string is your favorite or the most likely probabilistic to happen. But we can also talk about simply, is there a pattern in the string? So this string also looks random, but it happens to be pi, so in binary. So it starts off 1, 1, which is 3. So you recognize that in binary. And you might think that you might say, hey, the bits of pi are random, so you shouldn't be able to compress it anyway. But Newton was certainly able to write Java code that could print out as many bits as pi in any accuracy that you want, right? So how could we encode? Well, the boy wants to communicate pi, and he could, instead of sending, trillions of bits of pi, all he has to do is send the short Java code, which prints all the bits of pi, and suddenly the receiver can run the Java code and get all the bits of pi, right? So that's an encoding decoding, and that's certainly compression because you have a small program which will do it. So in general, we say, you have one string and we want one really long string, and we want to ask, is this string kind of random? Or is it special? Does it have some pattern that we can take advantage of, right? Where does this come in? Partly is that if I gave you an image of a cat versus face versus bicycle, right? Is there some pattern there that we can learn versus is it just random information? All right, so I'm going to say a string has Kolmogorov complexity R if there is a Java program that outputs it, and that Java program is described itself by R bits. And why is that useful to us? I'm saying that gives us compression. Why? Because you could have some crazy string, and then what you do is you communicate the R bit needed to tell me the Java program, and then the receiver runs the Java program and gets the bits back. right? So as long as R is smaller than the number of bits in the message, then there's compression, right? So that then asks the question, well, what fraction of n-bit strings, right? What fraction of n-bit strings can you do some compression? Can you go from needing n bits to n minus k bits? Can you save on k bits of communication? All right. Well, it's a simple counting argument that there are 2 to the n possible message strings of length n, and how many Java programs are there that are described with n minus k bits, right? There are fewer of them. And so you divide, and it tells me that the fraction of messages that you can even save only k bits is really quite exponentially small in k, right? So it has to be very special even to save k bits. But suppose you want to save half the bits, right? You want to communicate n over 2 bits to get your n-bit message across, and n's really big. Well, then it gets to be, as n gets big, the fraction goes to 0, right? You really have to be, pi is really a special value so that you can communicate it with a constant number of bits. All right, so now let's try some other things. Suppose we had an image and we wanted to compress it. Well, the obvious method is it has a lot of pixels, and you just write down the bits, the color for each pixel. Takes a lot of bits, right? But this image is not random, right? It's not every pixel wasn't independently chosen to be a color. There's a lot of structure to it. There's a lot of green, for example. And so because of that, something like JPEG can do a lot of compression. All right, so let's get to the example that is relevant right now. Is suppose what we're trying to communicate is some really a sequence of 10,000 either face or bicycle, right? Each one is kind of a bit. Face, bicycle, bicycle, face. It's a long sequence. And if all of these are kind of random, if they're all chosen randomly, to communicate 10,000 of them clearly takes, as we said, as Shannon told us, it takes 10,000 bits to communicate 10,000 labels. All right. Right, no compression is possible. All right, so now let's shift over to pretending that we have 10,000 images that are fixed, and both the sender and the receiver, everybody knows them, has a copy of these images. And right, and so then the supervisor is going to give us the labels of these images, right? So everybody knows the images, and then the supervisor tells us which one's a face and which one's a bicycle, and that needs to be communicated from the one boy to the other boy, right? And so we might say, how many bits does he need to communicate? And the obvious, well, maybe it's not an obvious answer. The one answer is none. He doesn't have to communicate any bits whatsoever. And why is that? Because with simple, maybe he can communicate a little instructions, but he can say, hey, you have all the images memorized. So you look at each one, and if it's a face, then say face. And if it's a bicycle, say bicycle. And that then gives you all the labelings, right? So that works great efficiency. But let's make it a little harder, where the receiver is no longer a human. The receiver is a robot. And the problem with robots is, until you train them, they don't know the difference between a face and a bicycle, right? So the robot has all these images, but doesn't know which one's a face and a bicycle, right? So how many bits do you have to communicate to him So he can figure out the sequence of face bicycle, right? And so the one you can always resort back to, you just tell him the 10,000 labels, right? And if these labels were really random, if there wasn't, this wasn't, you know, an image of a face at face, but if there were random labels, then you couldn't do any compression, right? You would have to send the labels, right? But maybe instead of sending him the labels, you can send enough bits along the line to teach him how to recognize faces and bicycles. All right, because he knows the images. So if you could teach him to distinguish faces and bicycles, then he would be able to solve the problem, right? So what is our setup here? As I say, we have a fixed set of images, and we've designed already the layout of our neural net. And then comes the supervisor tells us the labeling. And we need to encode that in some ways, right? And she hasn't given us a random labeling. It's specifically, she labeled the faces and the bicycles, and there's patterns, right? Faces look different than bicycles. So there is some pattern to this. And we need to somehow encode those to send it along the line so that the robot can decode it. And here's one possible way to encode, all right? What we do is we take all the labels, and we know those are supposed to be the outputs when the images are the inputs. So what we're going to do in order to encode is we're going to do machine learning and learn the weights, right? We're going to do gradient descent, and we're going to find these weights. And so that's the encoding process. Now, so what's sent along to the receiver are those weights. And then the receiver needs to decode. And how can the receiver decode? Well, he has the images, he has the weights. So he just has to run the neural net on all of the images with those weights, and it covers the labels, face and bicycles. And so that's compression, right? All right, so, as actually I said it was compression, but we haven't checked yet. When is it compression? It's compression when the number of weights, or at least the number of bits to describe these weights, is smaller than the number of labels, right? It has to be, to compression, this is a smaller number than this number. All right, so that's just a little bit about communicating and compression, and maybe it helps with machine learning and maybe it doesn't. But let's go on to understanding packed learning, which I think was, as I said, it was a hot topic in the 80s when I was a grad student. All right, so what we're gonna believe here, the assumption is that the universe has some fixed underlying distribution on images. So when you choose your random training data, it's chosen from that distribution of images. So you're going to randomly choose some images to be your training data. And then you're going to do machine learning. Using those images, you're going to come up with some machine that gives really good answers for the training data, right? And we're going to add this caveat that it does it without simply memorizing, right? And we'll have to define, well, we've kind of defined already what that means, right? We'll have to see how it fits into the proof, right? And then what we can prove, and what we will prove today, is that with high probability, the machine that you just found will also do well on images it's never seen before. And why is there any hope, right? If this was just a worst case image, then there's no way it would be able to guarantee an answer, or at least with any probability. But what we're using here is that this new image that you haven't seen before is going to be drawn from the same sample space. It's a random image from the same universe from which the training data was taken. All right, so the hope is that when you choose your training data randomly, it somehow represents the general data, right? Because you chose it randomly. And certainly in sort of the law of big numbers is that when you do something random a large number of times, you choose a lot of random images, then somehow you expect it to be close to the expectation, right? All right, so let's sort of capture that same statement in a slightly different way. It might not even be recognizable from the previous statement, but it's going to be the same. All right, so what we're going to do is there are many machines depending on all the weights, right? You put different weights on the machines, you're going to get different machines, and let's fix one machine with one weight. And we don't know, this machine might do really well, it might do really badly. We don't know anything about the machine. All it is we got some machine, right? And then we're going to randomly choose our training data, right? With this fixed machine in mind, we randomly choose training data. And the question we ask we're not going to ask whether this machine does well or doesn't do well, right? Because we don't know that. It's just some machine. But what we want to know is, does the training data somehow give an accurate picture of how well this machine does on general data? All right, because we can look how well this machine does on the training data, but we can't look to see how well this machine does on general data. But if the training data has the property that it gives an accurate picture of how well it does, then we're happy with our training data, right? From our training data, we can learn. And so what we're going to be proving is that the probability that the training data isn't a good representation is small, right? Exponentially small. All right. So we're going to first do that for a fixed machine. And then we're going to say, hey, there are not very many machines. Why aren't there very many machines? Because they're described by a small number of bits, right? Each machine is described by these weights. They're only in bits in these weights, so there aren't too many machines. And then if you know the union bound, right, we can translate these two pieces of information into saying the probability that the training data is not only a good accurate picture, give a good accurate picture of how well this machine does, it simultaneously gives you an accurate picture of how well each and every machine does. All right. So, and this is called uniform convergence. And why is, if we have this property, then we're really great, because the training data will tell us how good each machine is. And then we can choose, when we choose the machine that works best on the training data, it also works best on the general data, because we have accurate information about how well each machine works. All right, are you kind of following this? Shanaz, are you coming along here?
Yes, I'm almost.
Excellent, excellent. You have any questions? Anybody have questions? Holler if you have.
Yeah. There was a question from the compression slide. So
Yeah.
do you want me to ask? Okay.
Sure,
So I think
sure.
Martin was asking that if you're talking about lossless compression, doesn't a JPEG lose information?
You know, I was hoping that nobody would ask that. we could redo the counts. If you don't need it to be recovered perfectly, then I mean, you can still do some compression even if you want it to come back perfectly. And then you can do even more compression if you don't need it to come back perfectly. And I figured we could redo those counts, but I don't think it won't add anything to. And in fact, we're here doing, our compression isn't perfect either, right? Because the machine that you learned won't get all the labels correctly, right? So
Danielle has a question as well, looks like, but before I give it to Danielle, Martin just wanted to make sure if you have any follow-up.
oh, Martin?
Yes. I
Do
think
you
he's
have any
saying he's good.
follow-up?
Okay.
Martin's
I think
good.
yes. Okay, awesome. Danielle, it's all yours.
Great. I have a question that it seems like you chose the machine before the problem was fully defined, and then you're using that assumption to say that, well, a machine of this size can only have a certain number of states, and therefore I have a proof. But it seems though that you've already chosen a priori in the beginning, just arbitrarily, a machine of a certain size. And that's not really it could easily not be a sufficient machine for the problem at hand. I'm misunderstanding something.
Right. I I think we're going to go over it again on a slide in a minute, but just to say, at the beginning, we have to say, we have to define a class of machines from which we're going to learn. And so we're going to, that will be, we'll specify the complexity M, and we'll have the set of all machines. And then there's two questions. The one question is underfitting. If your machines aren't complex enough that it can learn the problem at all, then it doesn't matter whether you have training data or general data. It just won't do well at all. So that's the one question: is your machine, does there exist a machine within your set of machines that will do well on your problem? And then a separate question is, if there's a machine in your class that does well on the training data, does it also do well on the general data? Did that answer your question, Daniel?
Yes, it does. Thank you.
Excellent. All right, so here, what does without simply minimizing mean, right? As we just said, we're going to fix some number of bits that we're describing, or values or bits that we're using to describe the weights. And we have to decide how much training data we're going to need. And if the machine is way more powerful than the amount of information in the training data, right? If you don't have enough training data, right? We have fewer training data than weights. Then I claim that you can always solve the problem, right? So Daniel was asking, how do you know you can solve the problem? Well, if the machine is complex enough, then I claim any problem can be solved. And just as an argument for that, here we have, suppose I have M values that I need to learn, right? M points here. How could I learn them? Well, one, I could use a table of size M. Simply, I write down the answers, right? I write down what's this value, what's this value, what's this value. With a table of size M, I can learn M values, right? Another option is, you might know that if you have M points, you can have an M degree polynomial that fits through it, right? So you could learn some polynomial that fits your data. And similarly, you can have a neural net that can solve the problem. And I gave just a little bit of thought to it, and I could come up with, if you have M hidden nodes, you could certainly learn about M data values, but that's, hidden nodes are more than weights, but let's not worry about that. All right, so the point is, if your machine's complex enough, then you can learn any problem, and that's great. but the problem is that you haven't learned anything about the data, you've just memorized it, and it might not do well on general inputs that you've never seen before. All right, so we're trying to find this bot, right? As we talked about, if you're over here, if the machines aren't complex, they just won't learn the problem at all. But hopefully we can come in here where we're trying to find where it's doing well in general, the general inputs. All right, so that was overfitting up here. And now let's go to the other direction. Suppose given the fixed number complexity of your machine, the number of bits, here I'm going to change it to bits, that you're using to specify your machine, then right, then you need more data than that, right? You need more training data, and so that compression is happening, right? So here we have D training data values, 10,000 data values, and we compress them maybe into only 1,000 values, and so that's where the compression happens. All right. And the advantage, as I've said, is that if you have to compress it, remember Shannon proves that if there was no pattern, right? If I took images and I assigned random labels to them, then an overfitting machine could learn it, but you couldn't compress it. You couldn't have a machine that had fewer weights learn random data. The only reason you can learn with fewer weights is if there's some pattern in the labels, right? Bicycles really are labeled bicycles, and they're different than faces, right? So once you compress, why were you able to compress? Is that you had to somehow understand that this image is a bicycle and this one's a face, and can recognize them. And so hopefully then you can use that information to look at images you've never seen before. All right. And so, as I say, we're trying to live in here. And what's happening in here, as Daniel was kind of saying, we don't know for sure whether a particular machine does well on the training data or whether it does well in the general data. What we're saying is if it does well in one, it does well in the other. If it does well in the training data, then it does well in the general, and vice versa, right? So this comes down to the statement I've said before. For a particular machine, does this training data capture the accuracy of the machine on general inputs, right? It could be that the machine doesn't do well in the training data and it doesn't do well in the general inputs, but that's captured in the training data. Or it could be the machine does well on both, and that's captured in the training data, right? So that's what I mean by here, that for any particular machine, if it does well on the training data, then it also does well on the general data, right? And let's add some numbers in there to quantify what we mean by that, right? Let's have some purple epsilon be the fraction, right? We have a particular machine in mind, and we're asking what fraction of the training data does it give the wrong answer for, right? So that will be our purple epsilon. And that reflects how well does the machine understand the world, right? Because it understands, I guess it tells you how well it understands the training data, but does it reflect in the world, right? So conversely, the blue epsilon is going to tell you how well does the machine do on general inputs, right? What fraction of general inputs does it give the wrong answer to? And that's what we really know about the world. And what do we want? We want for these, if one's small, then the other small, and vice versa. We're saying that the difference between these epsilons, and you see there are absolute value signs, so they could go, you could do better or worse in either direction. But the difference between these is bounded by some epsilon, right? And that's what I mean by that statement here. And this is also what I mean by the training data is accurately representing how well the machine does on the general data, right? Because if it does well in one, it does well in the other. If it does unwell in the other, it does well in one. So, so what will our theorem be? Our theorem says for any epsilon, you choose your favorite epsilon, and then you randomly choose your training data, right? Then the probability that this statement here, right, is true for absolutely every machine is somehow exponentially small, right? So here we're making a statement about every machine. For every machine, we have this is true about that machine with respect to this training data. All right. And again, I said that's uniform convergence. Now let's put in some numbers, right? There's an epsilon here. How does the epsilon come into it, right? The epsilon is needed for the relationship between how much training data you have and how many bits to communicate the machine. And then when you have that epsilon there, it gives you an equation in terms of the data, right? The delta here, right? We bound this probability by something exponentially small. All right, now before we try to prove this lemma, this theorem, let's think about how it's useful in the real world. All right, so it's, I keep saying the same thing over again, but suppose you've all right, so again, like we talked with Daniel, we start with the idea that you've decided what your machines are going to look like and how many bits are you going to be describing them with, right? So we have a class of machines. And given this class of machines, we then have to choose how much training data we're going to use. And the requirement that we have written down before is that the amount of training data has to be bigger than the number of bits here divided by epsilon, right? So 1 divided by epsilon squared is a big number, right? So D has to be bigger than a really big number times n, right? And that's our requirement. All right, so now what do we do with that? Now within our class of machines, we manage to find a machine that does well in the training data. Then it will follow that it also does well in the general inputs. And we can quantify that by what fraction of the training data does it give the wrong answer for over to what fraction here. And you'll see that on the general data, it won't do more than an epsilon fraction worse than it did over here, right? So conversely, suppose you know that out there is some machine that works well in the training data. Works well on the general data. Right? Your machines are powerful enough that there is a machine that can do the job. Then it follows that there exists a machine that does well in the training data, right? And similarly, we can quantify it that how well it does on the training data is no more worse than an epsilon worse than what it did over here. All right. And you see there's a plus epsilon in both directions. It's because we have this absolute value sign, right? Now, this just says that there is a machine that works well in the training data. So we only can hope that gradient descent manages to find it, right? Or maybe gradient descent doesn't find that machine, but it finds another machine that's good. All right. Now, what else can we say about this theorem that might be helpful? Well, you'll notice that the human brain manages to distinguish between faces and bicycles perfectly well, certainly within some epsilon fraction on the general inputs, right? So this is a problem that's solved by humans. And my belief, at least, is that the human brain isn't really fundamentally different than a neural net. And hence, what does that tell me? Is that if the brain can do it, then a neural net can do it. And then we use our theorem that says if a neural net can do it, then it will do well, right? If a neural net can do it on the general inputs, then it can do it on the training data. And again, hopefully we'll find it, right? So that maybe kind of explains why machine learning has been so successful, is because the brain can do it, and hence there are neural nets that can do it. And are we able to find them? All right. One thing that I want to note that this result doesn't talk about, which makes it more useful, is we never mention how big is the set of the general input. That's never comes into it. And in fact, the values, the purple and the blue values of epsilon don't come into the theorem. All right. I mean, they come in here as the application of the theorem, but not in the statement of the theorem. All right. So are there any questions? Are people following along? All right. So let's do a little probability theory. Everybody should know Chernoff bounds, and this is another one I didn't know of, but we need them in this proof. So what we're stating here, this is just the binomial distribution, right? If you have a coin that has the probability of getting a heads is a quarter, and you flip that coin 20 times, then you should all know that the expected number of heads is given by this equation, and you expect to get 5 heads, right? So here's, right, the most likely is 5, and somehow the average is 5 in this distribution. All right, so now what will Chernoff tell us? Chernoff says, well, you're not going to get exactly 5, right? You're going to deviate from the expected value some. But he says the probability of deviating too much is exponentially small. And what do we mean by too much? Well, the probability of deviating from the mean, right? Here's the absolute value sign. So what's the probability the number of heads I get deviates more than some epsilon fraction of the mean from the mean, right? The probability I deviate from the mean by some epsilon fraction of the mean is exponentially small, right? So that's Chernoff bounds. And the problem with it is it has this blue epsilon everywhere, or at least has a blue epsilon over here, and we don't like that. All right. So Hofting, I guess we said it, evidently has a version of Chernoff bounds without the epsilon in it, in the probability. All right. So to do it, let's not talk about numbers anymore. Let's talk about what fraction of the heads that of the coins that I flip come up heads, right? Well, the expected number of that fraction is clearly the blue epsilon, right? Because it's blue epsilon is the probability of getting a head. So the expected fraction of heads that I'm going to get will be that blue epsilon. And so that's what we expect to get. Well, what is the fraction of heads that I do obtain, right? Let's have that be the purple epsilon. And we can write a really simple equation that says, well, the probability is exponentially small that the fraction I obtain deviates from the expected fraction by more than some epsilon, right? Right, so you don't expect to deviate very far. And right, that's the Hofting version of Chernoff bounds. And I have notes on probabilities if you want to look at them. So let's get back to our packed learning. All right, what is packed learning? What were we saying is fix some machine. All right, you have lots of weights, so there are lots of machines. Let's fix one setting of the weights, so we have one machine. And then with that machine in mind, we're going to randomly choose some training data. And what do we want to bound? We want to bound this probability that that the training data that we choose reflects how well this machine does on general inputs, right? This is the probability we want to bound. And so we're gonna bound it pretty much proof by picture, right? We're gonna draw a little picture here and then we'll put the answer down. All right, so what is this? This is the set of all possible inputs. According to, remember I said there was some underlying distribution that the universe imposes. So this might not be a uniform distribution, but it's some distribution on the set of all inputs. And what do we know is that these are the inputs. We have a fixed machine in mind, right? And these are the inputs where that fixed machine gives the wrong answer. And we've quantified that the probability of getting such an input, right? The size, the area of this little circle is going to be the blue epsilon. Now, as I've said before, this blue epsilon may be a big number or maybe a small number, right? We don't know how well the machine's doing on the all the inputs, right? But it's some number, and there is there's the number that it is that represents the area. So now, once we have that set up, we're going to randomly choose our training data, right? So there, we just randomly sample from this universe of inputs. We choose that input, we choose that input, right? We choose various inputs randomly. And so then we can ask, well, what fraction of our training data is going to fall in this circle, right? Because remember what the circle is. It's those inputs on which the machine gives the wrong answer. So if a training data falls in the circle, it will be a training data that gives the wrong answer for this problem. And so what fraction of the training data do we expect to fall in this circle? Well, it's the blue epsilon, right? Because that's the definition, that's the probability of landing in that circle, right? But let's denote by the purple epsilon what fraction of the training data actually falls into that circle, right? It could be more, it could be less. It's all based on you're randomly sampling from this distribution, right? You're sampling D different training data items, right? But if D is a big number, right, then by the law of large numbers, then you are your training data will kind of represent the set of all inputs. How we'll represent it is by the fraction that falls in the blue circle is about the same as the fraction that should lie in the circle, right? And so we can write that down using our Hofton sort of statement, which says that for this particular machine, the probability that the blue and the purple epsilons deviate by more than the red epsilon is exponentially small, an amount that only depends on the red epsilon, right? Because remember, the blue epsilon could be big or it could be small. We don't know anything about the blue epsilon, right? We're just saying the probability that we deviate far from that isn't very big, right? We're going to, the training data is going to represent how well the machine does on general data. All right, so there we have bound this probability by that exponential small number. Everybody kind of follow that? Any questions? If not, then we will go on to counting machines. All right, how many machines are there? Well, we stated that the complexity of the machine is going to be M, and we've sort of said that in this dialogue, that's going to be how many bits does it take to describe the machine? And that tells us that there can't be more than 2 to the n machines, right? Because each binary string of length m is going to describe one of these machines. And so that bounds how many machines we have, right? We're just doing a counting argument, just like we did when we were saying how many Java programs can be small, right? Similar argument. We're just doing a counting argument. How many machines are there? All right. All right. So let's convert from machines to people. I don't know why. It seems like, all right. So suppose we're going to do the union bound. All right. So if you don't know the union bound, you should know it. It states, suppose you have 100 people and each person gets sick with some probability 1/1,000. What's the probability that at least one person gets sick? Now, one thing I'm not telling you here is whether there's dependencies or independencies between the people, right? Maybe if one person gets sick in your family, then more people in the family are likely to get sick, right? There could be any weird dependencies here. It's funny that I have 1/1,000 here. I made these slides years and years ago, but it's funny that it's 1/1,000 because that's the probability you die of COVID. But anyway, the probability that somebody gets sick is the number of people is bounded above by the number of people times the probability that one of them gets sick. And how can we prove that? Again, we can prove it proof by picture. Here's the set of all possible universes, right? So we're going to, when we flip our coins for the probability, it's like throwing a dart in this box, which will select which universe we live in. And so the area of this box is 1 because our overall probability that we land in the box is 1. Then for each person, let's consider the first person. In which universes does the first person get sick, right? He's going to get sick in the ones in the red circle, right? So if you throw a dart at this square randomly, if it falls in the red circle, then the first person gets sick, right? And what's the area of this circle? Well, it's the probability that he lands in this circle is 1/1,000, right? So the area of this circle is 1/1,000. Now we do the second person and we do all the people, right? Here's the circle for all the people. And the dependencies come in is we don't know whether they overlap more or don't overlap more. We don't know how much they overlap, right? If they're highly dependent, then they overlap a lot. If they're inversely dependent, right, then they don't overlap. Anyway, either way, what's the probability that somebody gets sick, right? It's the probability your dart lands in one of those red circles, and that equals the total area covered, right? So the sum area of all the circles can't be more than the number of circles times the area of each circle, right? So that is the union bound, which is good to know. And quite frankly, if the people get sick independently, then this is a pretty close, and this number is small, then this is a pretty close to the actual probability somebody gets sick, right? It comes down to what's the probability 2 people get sick, right? All right, so anyway, let's go back to packed learning, right? Remember what we did before is for each machine, right? For a particular machine, we bounded the probability, but we now need to bound what's the probability? We choose our data, our training data randomly, And each and every machine is represented by the same training data, right? We don't have a different training data for each machine. Remember, we focused on one machine and randomly chose our training data, but now we want the same training data to work for each and every machine, right? So what's the probability that our training data works well for each and every machine? Well, we're going to do the union bound, right? So it's the probability that the training data works for a particular machine times the number of machines, right? That's just the union bound. And then we bound that already in our one talk, and then we bound the number of machines. And remember that our rule from compression was that m was less than this factor here. So we can take this m and convert it into this. And here we have -2 of those, and here we have a +1 of those. And so it works out to being just that. And that was our result, right? And just a repeat, right? This is the probability that we're going to say something goes wrong, right? If our training data doesn't accurately represent one of our machines, then we're in this bad exponentially small probability, right? But if that doesn't happen, right? If we don't hit this bad event, then with high probability, right, i.e. with probability 1 minus delta, which is high probability, right, our training data accurately represents all our machines. We have uniform convergence. We have that for every machine, if it does well in the one machine, if the machine does well in the training data, if and only if it does well in general data, right? And it's just what we said before. If it does well in the training data, then it does well in the general data. If it does well in the general data, it does well in the training data. And that is the proof of that. So, any questions about that proof? Or am I losing people? How are you doing, Shanaz?
Yeah, I'm going to say I'm all right.
All right. It'll be on the test.
Oh my God. Then I'm not all right.
No, that was a joke. We don't have a test on this. All right. So you might have heard the term VC dimension. It's a measure that people in theory use, and it's a measure. I used it in my master's thesis. For whatever that's worth, I use the VC dimension. So anyway, let's define VC dimension. So as we were doing before, M is somehow the complexity, some measure of how you have a set of machines, and we wanted to find something about how complex that set of machines is, right? The set of all neural networks, how complex are they? Well, before we defined M to be the number of bits to describe a particular one, right? So it was the log of the number of them here. But we're going to get rid of that, and we're going to define a new definition called the VC dimension. And let me define it for you. So given, right, we're given a class of machines, right? This is a set of all neural networks that have a certain number of nodes and a certain number of layers, right? We want to know how complex is that set of machines. And if you want to know what VC stands for, don't ask me to say it, but it's the names of two people. And it's going to somehow measure how much freedom there is, degrees of freedom within this set of machines, right? Are all the machines more or less the same, or really is there lots and lots of flexibility of what these machines do? All right. So it's defined to be a number M, right? M is the VC dimension. It's the biggest value M, such that if you took any set of training data. You can take any training data, right? This is one training data, another training, any set of training data. And then given that set of training data, you looked at all possible labels of the training data, right? You fix the training data, right? So this is some image and this is some image. Each of these is some image. And this is sort of worst case. You get some set of images. And then what you do is the supervisor is going to give labels to those training data. And there are let's say each label is a bit. So there are 2 to the m labels, right? You're labeling each image as it is a face or it isn't a face. That's what we're labeling it with a bit. So there are 2 to the n possible answers that she could give, right? And what we need is that for each possible answers that the supervisor could give, there does exist a machine that could give you those answers, right? So it basically, it says this set of machines has high VC dimension is if you could give me any set of images, that many images, and you give me, right, that we're gonna feed all of those images into the machine, and we want to know how well does the machine do on those images. Well, there is a machine that could learn any possible set of outputs, right? That's the VC dimension. And why is it interesting? It's interesting because generally it's much smaller than the number of bits to specify the machine, right? They're related, but it tends to be much smaller. And the same proof goes through, and the proof's not that different. So my vote is we don't, I have the slides here, but my vote is we don't go through the proof because 1, it's a little harder, and 2, it doesn't use any new techniques. It's just sort of the same proof, a little harder. But the slides are there if you want to look at them. And that's all I have to say about general learning. So if people have questions, we can talk about them. If people want to stop, we can stop. If people want to find some other topic, we could talk about something else. Any thoughts?
Thanks, Jeff. I don't see any new question on the chat box, so guys, please feel free to either raise your hand or write it down on the chat box. Danielle has a question. Danielle, please unmute yourself and go ahead.
A great presentation.
Thanks.
Yes, thank you very much. I have a question for you, and I know, and I'm just going to assume that you don't really have a deep connections to the Tesla folks who are trying to do the automatic or self-driving cars.
Right.
And they have been very, very stymied by the complexity of the number of examples that they have to have for their
Right.
training data.
Right.
And how did now Elon Musk, of course, is hired at very, very great expense, like the Uber PhDs, to solve this machine learning problem.
Right.
But they are years behind schedule. What do you think? There's a fundamental problem with machine learning as we have it today?
You know, I don't know. I did see a talk by Hinton. It was a professor at U of T when I was there, and he's a big guy in machine learning. And a couple years ago, he gave a talk at York, which was quite fascinating, and about what machine learning might do, what the brain might do, and what we might do future. Is you need to, right, the brain, when it sees this pixel and this pixel, it knows that they're next to each other, right? But the neuron that's not using that information, right? There's no sense of locality. And the one way you can get locality is by convolution nets, which we're going to talk about later, and which says, you know, if you learn how to find a cat over here, you can use those same weights to learn a cat down here in the weights, and right. So, but that just is translation, right? So Jeff Hinton is saying, how can we have the weights of the machine somehow learn a three-dimensional object that is still works under rotations and under, right? So there are lots of things that the brain might be doing that we just don't take advantage of, and that's beyond what I can say here. My understanding is that the self-driving cars are doing really quite well when they drive down predictable streets. It's when it starts snowing and there are potholes and that it gets to be harder.
Thanks.
Thanks, Daniel. I have one more question from Mike. He's asking, is there any an existing specific way of finding patterns in an image that will improve the recognition before sending the data into your machine learning machines?
You want to kind of pre-process the image so that you will recognize whether it's a cat or dog easier once you're learning? Is that the question?
Yes.
One thing I have learned, which I think is kind of cool, suppose you have two completely different learning projects, right? You want to know, is it a cat or a dog? And you also want to know, is it big or small? Is it red or green? I don't know. Different tangential questions about the same image. And in some ways, you think they're independent questions, but it turns out that if you get the same, if you learn both of these, all these various problems simultaneously in parallel with the same machine, then it does better than solving one of the machines independently, because the intuition there, the thing is somehow it needs to learn that, hey, that block is an object that we care about, and I can learn that from the fact that I'm identifying it to be a face, and I'm learning that when I'm learning whether or not it's blue, right? So so in some ways it might answer your question, because the reason I said it is because if I were to look at the image and decide, is it a face or a bicycle, if you were then to ask me a different question about it, what I learned in the first learning could be helpful in my second learning. Was that a useful answer? It was. I made it up, right? So don't quote me on that.
I'm just keeping an eye on the chat box to see if Mike responds, but so far nothing.
Right. And certainly there can be, I did take a course on this high level course from Tsotsos up at York, and it was so high level, he never talked about actually what was happening, but he would say, well, you first pre-process it by deciding to break it up into well, what is a cat, and what is this object and what is that object, and then you feed each of those objects into something, but then you need feedback based on saying, hey, were you able to, if you weren't able to recognize it as a cat, maybe you partitioned the information wrong, right? So there's also, that's kind of pre-processing too, right? It's all information's flowing around in some way that I certainly don't understand.
Right. Mike has a comment that sounds good, but I'm thinking about it the way a human brain has a facial recognition system built in, like a preprocessor built in. Right.
Well, I don't know if this is going to answer your question, but one major difference between learning to do something in machine learning versus for a 5-year-old to learn it, is the 5-year-old is only going to need a dozen examples of cats and dogs, and she will figure out what the cat and a dog is, while the machine learning needs hundreds of thousands of examples of cats and dogs, right? So you might say, well, the human's doing better than the machine learning. But I do say that that's not really fair, because the human brain has been doing machine learning for the last, I don't know, hundreds of thousands, billion, I don't know how many years we've been learning. So I do think that built into your brain when you're born is the ability to recognize faces, right? So in some ways the child isn't learning that after they're born. They were born knowing how to recognize faces. I don't know if that answered any of your question either.
Thank you. I'll wait if Mike has any. Mike is saying thank you. So I'll move on to Manoj. You can unmute yourself and ask your question.
Yeah, I think my question was answered, so thank you.
All right.
Awesome.
Excellent.
I don't see any more questions, Jeff. So thank you so much. Again,
All
it
right.
was a lovely presentation.
All right. I hope people were able to follow it okay. And if you haven't seen, I've been putting together my own webpage of where you can. I'm going to put the talks when they come around. So if you go to machine learning, here's the list of the talks, and I'll put the videos and the slides and things that people want.
And again, I also shared the link for the next 3 sessions, so please feel free to use them. And for the video link for last week's, we're just in the process of uploading. So again, once it happens, Jeff, I'll share that with you. I already poked Dustin about it, so I'll share with you and let you update this website.
Excellent. And so next week, we're going to be doing reinforcement learning, which is, I'm basically going to tell you everything I learned in grad school about the topic and how to play Go or make a martini.
Right. Shahnaz, no, there is actually have a session next week. Maybe I got too excited and thought December is coming very soon. So that's why I didn't put it. Hold on. I can put it there.
For this one, I have a link. See that? Somebody gave me this link.
Yes.
There it is. That one's linked.
Perfect. Again, I just got excited. I thought we are really in the after mid-November, so Christmas is coming. I just got excited.
Yeah. All right. Well, thanks everybody. And I personally have never done practical things with machine learning. And with Shahnaz here, we're in a class and we're trying to teach it. So before I can teach it, I have to learn it myself. So I was busy coding Python all day. And anybody wants to talk about that, we could do it as well. All right, so let's stop.
Thanks a lot, Jeff. Again.
Thanks so much, everybody. And hopefully we'll see you next week.
Thank you, Jeff.
Thank you, everybody.
Have a great evening.
Bye.
Bye.
Bye.